Yeah, this is a fun one. Okay, so let's say, for example, if we wanted to know, does the integral from negative infinity to infinity of 7x e to the x over 6 with respect to x converge or diverge? And if it converges, what does it converge to? Hopefully you started this on a fresh sheet of paper because it's kind of lengthy. Just a heads up. Okay. Now with this one, instead of rewriting it first, I'm going to integrate it first, and you'll see why, hopefully. So first, we'll just figure out the integral of 7x e to the x over 6 with respect to x. Okay, so we'll let u equal 7x, which means our du is equal to 7 dx. We'll let our dv equals e to the x over 6 dx. Let me separate that a little bit more. Which means our v will equal the integral of that, which is 1 over 1 over 6, which would give us 6 e to the x over 6. Okay, so our integral of u dv equals uv minus the integral of v du will give us uv, which is 7x times 6 e to the x over 6 minus the integral of v, 6e to the x over 6 du. Oh, where is it? Ah, there you go. 7 dx. All right, so we'll just go ahead and simplify it by combining what we can. So 7 and 6 is 42x e to the x over 6 minus, 42, we can just go ahead and bring that out to the front, e to the x over 6 dx. Okay, so we end up with 42x e to the x over 6 minus 1 over 1 over 6, which again is 6. So 42 times 6 is 252. So we end up with 252 e to the x over 6. All right. And that's the reason I waited, because now if we rewrite it, 7x e to the x over 6 dx, and we make that equal to, and you can pick any value between the two. Like I said, I always pick 0 just because it's easier. You can make it from negative infinity to 4, 4 to infinity, doesn't matter at all. Say from negative infinity to 0 of 7x e to the negative x over 6 dx plus the integral from 0 to infinity of 7x e to the...
It's just x over 6, not negative x.
Okay, I don't know why I put that negative there. I know it didn't sound right when I did it. X over 6 dx. Okay, and you just rewrite both of them. So if we rewrite both of them, we make the limit from a to 0 as a approaches negative infinity. So That 0 looks, clean that up some. Of 7x e to the x over 6 dx plus the limit from 0 to b as b approaches positive infinity of 7x e to the x over 6 dx. All right. So we already solved the integral. That's why I wanted to do that first, because we integrate those, that's just equal to the limit as a approaches negative infinity of the integral that we already solved, 42x e to the x over 6 minus 252 e to the x over 6 from a to 0. But that a looks a little bit like a 9. There we go. Plus the limit as b approaches positive infinity of 42x e to the x over 6 minus 252 e to the x over 6. From 0 to b. Bless you. All right, give you a few seconds to catch up, because we're nearing the end of the sheet of paper. So we'll be continuing on another sheet. So if you want to start on a new sheet, feel free, because it's going to run over. Okay, so now we just apply the fundamental theorem to both. Okay, so that's going to equal the limit as a approaches negative infinity. If we plug in 0, this just becomes 0. So 0 minus negative 252 times e to the power of 0 is just negative 252. Minus, if you plug in a, just replace every x with a. So you have 42 a times e to the a over 6 minus 252 e to the a over 6. Clean that up a little. And it's going to be a bit of a squeeze here. Plus, do the same thing here. The limit as b, see all that room I wasted? B approaches infinity. Just replace every x with b. So you have 42b times e to the b over 6 minus 252 e to the b over 6 minus, if you plug in 0, that disappears, and that just becomes negative 252. There. All right, so we're going to go ahead and just distribute our limits to both of those. These two we're going to keep together. We're not going to separate them, and I'll show you why. Because I actually did it by separating them and by keeping them together, and keeping them together was just a lot easier. Okay, so you have the limit of negative 252, which we already know is just going to be negative 250. Oh,
Can you move it up?
oh, sure. Nope, no problem. As a approaches negative infinity, okay, minus the limit of 42, and actually we're going to factor out the 42e to the a over 6. So 42e to the a over 6 times a minus 6, because you know 42 times 6 is 252. as a approaches negative infinity. And put a bracket around that whole thing. Plus, oh, I know I didn't mess up that fast. The limit as b approaches infinity. Again, we're going to keep all of that together. So 42e to the, this one's b over 6, times b minus 6. Actually, minus negative, that becomes plus. The limit of 252 as b approaches infinity. Leave that up there for a few seconds. And we're going to continue this on the next page. I'll leave that up and write down where we left off. So limit negative 252 as a approaches negative infinity. There we go. All right. Anyone still writing? All right. Oops. Okay, so now we just have to do each individual term and find the limit for each one. Okay, so we know here that's already going to be negative 252, and this is going to be positive 252. So really, those two just cancel out. Okay, now for this one, we'll kind of do this separate. Yeah, it should be enough room. Okay, so if we actually did plug in negative infinity, we'd end up with limit as a approaches negative infinity 42e to the, not negative, a over 6 times a minus 6. If we plugged in negative infinity times minus 6 is still negative infinity. So that actually becomes negative infinity. And if we plug in negative infinity, that becomes 1 over e to the a over 6 as a approaches infinity. So it just gets bigger and bigger and bigger, which means this approaches 0. Okay. So it's in the form where if we tweak it enough, we can use L'Hopital's rule. Okay, but here we can't use it yet. So no L'Hopital's rule. No L'Hopital's rule for you. Okay, but if we rewrite it, let's say as the limit as a approaches negative infinity of 42 times a minus 6 over e to the negative, I'm about to write b. Uh-oh. A over 6. E to the negative a over 6, you just bring that up, it becomes e to the positive a over 6. So we just tweaked it a little bit. Use those negative exponent rules. Okay. So we know if we plug in negative infinity, negative and negative is positive, so you have e to the positive infinity here, which becomes infinity. And here, again, infinity minus 6 is still going to give us infinity, or negative infinity, rather. So we have negative infinity over infinity now, which means we can use L'Hopital's rule. All right, so that gives us the limit as a approaches negative infinity. Derivative of 42 times a minus 6, you can just factor out the 42. And derivative of a minus 6 is just 1. Over the derivative of e to the negative a over 6, that looks like a 9 and it's throwing me off. There we go. Okay, so that's going to be negative 1 over 6 e to the negative a over 6. Which, if we multiply the numerator and the denominator by negative 6, that disappears. So it just becomes 42. Uh-oh, forgot my limit. I'll write it underneath since we're running out of room. So as a approaches negative infinity of 42 times negative 6 over e to the negative a over 6. Okay. Now after all of that, if we plug in negative infinity, we end up with positive infinity over 6. So e to the positive infinity just gets bigger and bigger and bigger. So we have a constant divided by a number that's getting bigger and bigger and bigger, which means the limit is equal to 0. So we did all that work to end up with 0. I hate doing all that work and ending up with 0 or 1. I don't know what it is about those two that just bugs me.
Just because they're like such small numbers.
I think this is all that work for something that simple, just
Right.
0. It's like I could have guessed 0, so. But yeah, that's the case.
50% chance.
Exactly. All right, so we know if we know this and this canceled each other out, so that's nothing. But here, we know it's minus 0, which you don't have to put the minus 0, but we'll do it anyway. And actually, just to get the whole steps, because I can see somebody sitting at home going, what happened to the 252? They'll say negative 252 minus 0. Now we have to do this one. And this one we know that's plus 252. So we can just put that one right there. And this one's not as bad. You can have like one little small box for that one. Because the limit, as b approaches infinity, of 42 e to the b over 6 times b minus 6, infinity times infinity, you don't have to tweak that for L'Hopital's rule. It's just infinity, a big number times a really big number is just a really big number. Yep, so that's just equal to infinity. Which automatically blows everything out the water. Because every other term can be convergent. But if you have that one divergent term, everything is gone. So it just so happens all those cancel out. So this is actually equal to infinity, which means it diverges. All right, so any questions on that one? Yes.
What if you were to have infinity and then minus infinity?
Oh, if you had infinity minus infinity, then you'd have to tweak it and somehow try to use L'Hopital's rule for it.
Okay.
Yes.
Where did the a minus 6 come from? A minus 6 and b minus 6?
You said
You simplify it like
the b minus 6.
You have b minus 6 and a minus 6.
Oh, from this step here, just before we applied the fundamental theorem, if you notice, we factored out a 42 e to the a over 6 here.
Oh.
And that gave us a minus 6. And we did the same thing here, but just a b. Does that make sense? Okay. Yes.
So is it as bad if you don't have to use integration by parts?
For this one,
For like
if you want, for like this particular step, because integration by parts isn't necessarily in the instructions, if you wanted to use the tabular method, you could.
Right.
So I wouldn't have a problem with that.
So you want to mark it down by your tablet?
No.
Cool.
The only time we get marked down is if you were supposed to use, if it says integration by parts, you didn't use integration by parts. But anything after that, where if it doesn't specify integration by parts, and you want to use tabular method,
And I think you said you don't do tabular method in the post? Or-
not until you learn integration by parts. Once you learn integration by parts, because a lot of people would use tabular method to avoid learning integration by parts.
Okay.
So as long as you know integration by parts and you want to use tabular method, I'm completely okay with it. All right, any other questions? All right. Okay, so now we're going to look at improper integrals at points of discontinuity. Okay, so let's say, for example, if we wanted to evaluate from 0 to 1
Math terms I can throw together in one lesson.
of dx over cube root of x. I remember when I was a student, I'm like, when does this end?
Right, never.
It doesn't. That's the sad part.
I'm just like, hey, all those other things you've learned over the past like 18 years of math,
Yep.
we're just gonna do that with integrals.
Yep. And it just builds up and builds up. And eventually you just get to class and be like, really? Just,
Like differential equations, you're just like.
oh, I thought differential equation was the end.
What's after that?
Oh man, what's not after that? You have complex
Differential
variables,
equations,
you
like
have
one
Fourier series, you have, it keeps
You're saying
going.
Fourier series?
Yep, Fourier series, you have wavelet transforms, you have, it keeps going and going and going.
Improper differential of.
Yep, you have
discontinuity.
advanced calc 1 and 2,
Gotcha.
and it keeps going. So, yeah, it doesn't end.
So those classes are for if you want to be a math teacher? Is that the case?
Most of those
Teaching at
are
advanced
graduate courses.
Graduate.
Yeah.
courses.
Yeah, I was gonna say.
Although a lot of them feed into things that aren't necessarily math as well.
Oh yeah, a lot of them, like Fourier series, a lot of engineers take
Engineers,
that.
physics.
When I
Yeah.
have to bring a brand new notebook to every single class,
That's why you gotta get that.
As long as I'm not getting
digital.
judged, then
Whether that's from me filling it or tearing it in half. I'm not-
All right, so we know here that it's not continuous at 0. So we couldn't plug in 0, which just wouldn't work. Since the integrand is not continuous at x equals 0, we rewrite it. So we have the limit as a approaches 0 from the right, from 0 to 1 of dx over the cube root of x. Okay, so we're not equaling 0, we're just getting really, really close to 0 from the right. Okay, so that's equal to the limit as a approaches 0 from the right. If we write that as x to the negative 1/3 power, we add 1, x to the 2/3 over 2/3. Oh, from 0 to 1. I don't know why I was about to write a. Oh, actually, it is from a to 1. Why did I write 0 here? That should be from a to 1. There we go. And why are my a's looking like 9s? That still looks like a 9. There we go. Close enough. Okay, so we can actually get that 3 over 2 and bring it out to the front. So a approaches 0 from the right. Times 3 over 2. X to the 2/3 from a to 1. Which is equal to 3 over 2 times we plug in 1, so we have 1 to the 2/3 minus a to the 2/3. Actually still have our limit there. And if you plug in 0 here, you just get 0 to the 2/3 power, which is 0. And 1 to the any power is just going to be 1. Oh, 1 times 3 over 2. Actually, should switch that over. Doesn't matter, but which is just 3 over 2. So it converges. We didn't ask if it converges, but we know it converges. All right, any questions on that one? Yes.
So when we're doing these on like a test or something,
Mhm.
you don't ask whether or not it converges or diverges. Do we just have to write the answer? Or do you
Yep,
want
you
to
just-
write
yep.
converges to everything?
Nope, you just write the answer and you're good.
Okay.
Only if it asks, does it diverge or converge?
Okay. So I know for the examples on the last section, you wrote converges to
Mhm.
for every single one. So
Oh, no, that was just one of those, just to drill it home. All right, any other questions on this one? All right. Okay, so let's say, for example, we wanted to evaluate the integral from -1 to 2, say of dx over x cubed. Okay. So we know it's continuous everywhere between -1 and 2 except 0. So that just means we have to go from -1 to 0, then from 0 to 2. So since the integrand is discontinuous at x equals 0, we rewrite it from -1 to 0, x cubed, or next to the -3 dx, plus the integral from 0 to 2 of x to the -3 dx. And since it's not continuous at 0, that's where the limit comes in. So the limit from -1 to b, as b approaches, oh, I'm about to write infinity, approaches 0, but in this case it's from the left.
oh, right.
Yep, because you're approaching from -1 of x to the -3 dx, plus the limit of the integral from a to 2 as a approaches 0 from the right of x to the -3 dx. Okay. So once we have it all set up, we just integrate, which is easy because they both give you the same integration until you start to plug stuff in. So b approaches 0 from the left, and this is x to the -2 over -2 from -1 to b, plus the limit as a approaches 0 from the right, again x to the -2 over -2, but in this case x, oh, did I put in, yep, a to 2. So if we factor out the -1/2, and I'll just put it right out front. So bring that up a little. Oh, I was rolling the dice.